I'm recording the screen right now, so make sure that I actually did that. Okay. So like I said from yesterday, right? So I already upload my second half of the lecture yesterday, and also as a compensations, also upload min last lecture about this topic. So you guys can like double check the topic, and also can like watching both the lecture to see uh, which topic you don't understand. You can like rewatch it. And today lecture is about linear algebra and calculus. I already upload the lecture note to the Google Drive, but you can have a short link right here. So first of all, let's open the, takes so long. Let's open the linear algebra notebook. So that is the main stuff that we talk about for the first half of today, and then later on we will talk about calculus, what is kind of important topic, very important topic, and we talk about that in the second half of this lecture. All right. Okay. Visa. So you can find our notebook inside this week. Okay, week 9 machine learning math. Let me open this notebook real quick. Okay. So how you guys feel about the math so far? Like yesterday, is it challenging? Is it difficult, or is it like doable? Does it make sense to you about the probability and statistic? Very good. We have like almost all the people understand that this concept. So today we're gonna go to this super important, I would say, critical topic. If you want to go deeper into machine learning, which is linear algebra and calculus. I know that these topics you guys already like learning during high school or uni, but you will like you be very like surprised that the majority of people actually forgot how to do calculus or linear algebra the moment they graduate from uni. Yeah. Um, so who actually here remember how to do linear algebra and calculus? Uh, yes or no? Who here actually remember all the rules for linear algebra and calculus? Yes. If you remember, no. If you don't remember, yeah. All right. So most people actually forgot all the rules for linear algebra and calculus. Don't worry, we're gonna go through them today. I just go through just the fundamental concept of them. I would not like ask you guys to do 10,000 different exercises, all right? Because that would be a waste of time. I think it's important for us to understand conceptually how this works, and that should be good enough. Okay, let's go through the linear algebra, all right? Let's connect this notebook to the cloud instances. Yep, it's connecting to one of the server in Google right now. Initializing, connected. Yep. So as you know that machine learning is to design algorithm, right? Technically, yesterday you already know that for machine learning, you need to build your own model. And that model hopefully gonna extract some useful information to make some predictions, right? Um, But at the end of the day, you need to optimize them. You have to optimize the process, how the model gonna learn from the data. And linear algebra is like a critical, super important in terms of machine learning because linear algebra gonna give us better intuitions of space in which our data live and how these machine learning operations gonna take place. And that was like the key point of this. Okay, let's go through this notebook together. First of all, okay, I have to run this as tall as code school. Okay, that's a bit annoying. Let's do that. Okay, connecting. Cool. Let's import the libraries here. So this library, you guys already know about that, right? You learn about NumPy, Pandas, Seaborn, Matplotlib. Okay, should be straightforward. So what is a vector? Okay, the keyword here is a vector. So at the end of the day, there's three main elements in the linear algebra. The first item would be scalar. I would type in the chat in case you guys don't know how to spell it. The first one is scalar. Scalar is a number. Okay, and the second important thing is vector. Vector is a one-dimensional array. And lastly, we have matrix is m by n dimensional array. Okay, so these are the building block of linear algebra. We have scalar, which is just a number. Could be 1, 2, 3, 4, 5. Could be a real number, right? 0.5, negative, whatever. A vector is just a one-dimensional array, just like this. So we have x1, x2, x dot 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 until xn. That would be n numbers. It belongs to real numbers, yeah. And all this will form a vector because the way we display our vector in a row like this, we call this one a row vector. Okay, this notation was consistent with Andrew notation. So I want to make everything consistent so that later on when we learn more about math or learn more about these machine learning concept, it'll be easier. And later on we will talk about matrix, which is just a lot of vectors together combined. So in short, a vector is elements of Rn, with R is a real number and N is number of dimensions. Like this. Okay, so we have X here is a 2 vector. This one is 1 and negative 1.3. These are two-dimensional array. Yeah, and let me run the hyperfunctions importance. So I run this. Okay, so this is how you display a vector on two-dimensional array. So you can see that a vector here is represented by a data point inside the data space. So x here is represented by this data point. Okay, the vector always start from the origin, which is 0, 0, and end up in the data point that is actually represented. You can see here, x is 2 and 2. So that is this point, and the vector is start from the origin point to that point for x. And for y, it was 1 over here and negative 1.3 in the vertical axis, which is here. And similarly, that y vector for y was starting from the original point and end up in that data point. Similarly for z, z was 1. So 1 here is the amount of scalar is pointing at the horizontal axis, which is here. And 3 is the scalar is pointing at the vertical axis, which is here. So 1, 3 would be at this point. So z was pointing from here to here. This is a vector for z. Okay, so far it's pretty straightforward. I'm sure you guys already learn about vector in high school. So let's move up. So is there any operations on vector? Yes, there is, right? So first of all, we have scalar multiplication. You can multiply a scalar or a number to a vector just like this. So imagine we have a vector x like this, and we multiply by a scalar a. So A multiplied by a vector x. X is two-dimensional array. So you can see that x1 and x2 just like this. And when you multiply a number by a vector, you are distribute that number and multiply by each element inside the vector. Yeah. So let's in this example we have in this example we have a x vector 1 1. Yeah. And then we want to display two vectors. The first vector is vector x multiplied by 3, and the second vector is just vector x. Let's display that. So this is the original vector x here. So after you multiply by 3, it's just scale the vector up 3 times. You can see here. So for the horizontal axis, it's multiplied by 3, and for the vertical axis, it's just multiplied by 3. When you multiply a vector by a scalar, it keeps the same direction here. You can see that this is the direction of x, and after you multiply by 3, it still have the same direction. Just the length of the vector is longer 3 times. Okay, as simple as that. What about additions? Can you plus two vectors together? Yes, you can. So imagine you have two vectors x and y like this, and x is x1 and x2, y is y1 and y2. When you have two vector, when you plus one and plus two vector, they need to have the same shape, right? So imagine if I have two-dimensional vector, I want to add them together, I need to have another two-dimensional vector. I cannot have like two-dimensional plus two-dimensional. It doesn't work that way. It has to be in the same shape. So you can see that the first element will be plus the first element of the second vector, just like this. Similarly, so this is element-wise operation. Is apply the operation for each of the element corresponding for two vector, just like this. Okay, these are pretty basic so far, yeah. So you have two vector, y1, and the second vector is negative 2, 2. Okay, so 1, 1 here. Let me try to find a way to draw it on the screen. Notations, I can draw that. Outline, draw. Test it. Show is too thick. I want it to be red. Okay, make it thicker. Okay. So this is your first vector 1, 1. This is your second vector negative 2 and 2 here. This is the second vector, yeah. This is the first vector. And then you want to plus these two vectors together. How do you do that? So obviously z is the vector that the result vector if you plus them, these two together. But intuitionally, how you do it? Just on this graph, how you do it? So there's a way to do it. First, you keep the same vector stable, just like this, and you move the second vector parallel so that the end of the second vector will hitting the top of the first vector. So if I draw x like this is my x. Right? So my new vector would be this one. Similarly, let's keep this one stable. And I want to move this y vector parallelly so that the end of the second vector hitting the top of the first vector, just like this. So this is my y. You can see that the end result of the vector after you combine these two vectors will be z. You can do that regardless here. Okay, so this is how you do intuitionally, but you can do it on paper too. Let me clear all my drawing. Yep. So this is how you do it mathematically. This is how you do it when you just draw a vector. Yeah, this is how you plus two vectors together. Okay, that is straightforward. What about subtractions? Can you do subtractions? let's say I have okay, I want to find x vector minus y vector. So how do I do it on paper? So you can do the oh, I need to clear that. Need to scroll down the screen. Uh, this is perfect. Okay. So I want to find x minus y. Yeah, is equal to what? X plus negative y. So negative y is just the vector that multiplied by negative 1 or just the opposite of that. So you can figure out now, we need to find the negative y, okay? So this is negative 2 and 2. So when you multiply by negative 1 to vector y, you will have this exact factor. This is your negative y vector. 2, negative 2 here. Okay, and to find this sum, you need to move the x parallelly. So you can see that this one is like 1, 1, and this is x. So your new vector after x plus negative 1 would be this vector. Yeah, this is your new vector. Okay. I hope you can understand how to plus and minus vector now. Let me know if you have any questions here, and we can move on. This is pretty straightforward, right? So far, it's like, oh, okay, I actually learned that in school before. Um, okay, let's spice things up. Yeah, of course, you're gonna multiply them. We're gonna talk about that later. Yeah, yeah, for sure. Okay, unique vector. So a unique vector is a vector with a length 1. Okay, so usually if you have a normal vector just like this u, and you want to find a unique vector of u or normalized vector of u, you can divide by the length of u. Let's say this is normal vector u. To find the unique vector of u, just divide by the length of u. Okay, and then let's say this is your vector. Your vector could be rotating like this, right? So in this, yep. So you can see that this is x. X, don't you agree that draw some things? Okay. Hmm. So x equal to this vector plus this vector, yeah? So this vector is just 3 times of I, and this vector is just 2 times of j. So it's a linear combinations between two vectors. Okay, I have to clear the notations. Clear. Yep. So you can see that, so for any vector, if you have two vector can like combination of them can represent by any other vector, you call them a basic vector. In this case, we're choosing horizontal unit vector, and the vertical unit vector j is as a basic vector. Okay, so these two vector with their combination linearly, you can representing any vector in 2D, just like this. You can choose any vector in 2D, and with the right number of x and x1 and x2, you can represent them using this coordination. So I will be the vector 1, 0, and j will be the vector 0 and 1. Okay, so let's bring them out. Yep, this is pretty straightforward, right? So x is can be represented by 3y and 2j. 3y plus 2j. Okay, that's x. So 3i plus 2j. This is your x. Okay. space. So you can say that. So because this is your basic unique vector, so there's linear combinations can written like this. So a x vector x plus b y vector, the combination can representing any vector in this 2D space. Um, to become a basis of vector space, they have to be linear independent to span the full space. Okay, let me go up here. Okay, so let's say I choosing this vector. Okay, can anyone tell me that this vector, let's say z, can you represent z based on I and j? Correct. So it's actually 1i plus 3j. That's cool. That's you are really quick in that. Can I choose another basics? Like for example, I don't choose I and j here. It's too easy, right? I can choose a different vector like this and another other one like let's say this. This is my new I and this is my new j. Can you find the combinations of I and j so that is equal to z? What is a way we can do it? Now it's getting challenging, right? Let's say I choose any other vectors to become my basic vector instead of like this I, the j, and choose a new I here and new j here. So it can be very challenging to represent z in terms of I and j here. So how do we do it? There's really easy, simple way to do it is you can extend. Okay, now this is a really bad example. Let me clear that. Let me choose a different color. Let's say I want to represent this point. Yeah, this is my z, and I want to choose two different linear combinations. Let's say this and this. This is my I. This is my new j. Okay. The way you do it is you can draw an infinite long line. Okay, it's like this, and you can apply the rules, right? So you can move this one parallelly along this line so that it's going to be cutting. This is your I. Yeah. So at the end of the day, how can we represent z here? So z equal to you can say that this factor j plus this factor I. This is j. This is your I. So this j equal to a scalar number multiplied by this basic factor, and this I equal to a scalar multiplied by this I. So I know that my z now equal to a number a multiplied by that z plus the b multiplied by I. Okay, I could figure out A and B just by the length of that. I can just find the length of this and the length of my basic vector and divide that to get my A and my B based on that. So what does it tell you? It tells you that for any dimensional space, you can choose any vector to be your basic vector. It doesn't have to be horizontal vector and vertical vector just like this. But make sure that they have to be uh, linearly independent. So okay, so what is example of something that not linearly independent? So this is linearly independent. This is linearly independent. So what is linearly independent? Let's say this is my I, the same. This is my J. Okay, so this combination between I here and J here are linearly dependent because they're on the same dimension, they're on the same line. So the span of this will be only one dimension, not two. Think about it. So because the span of these two, the combination of these two could be never two dimensions. So that's why it cannot be represented um, for any point in 2D. It has to be in 3D. Yeah. So this is a bad choice for basic vector. But anything else is fine. Anything else is fine. Anything else is fine. The combination of them will span the whole 2D vector. Okay. That's the idea of that. Okay, that's the idea of linearly independent and linearly dependent. Okay, now is a time for multiplications. Okay, yeah, Wang Cheng actually asked about that. So we have a dot product here, okay? So to find a dot product of two vectors, you are simply multiply, it's actually element-wise multiplications, yeah? You can just multiply each of the element together. So let's say I have A, B, this is my first vector, and C, D. This is my second vector. So if I do the dot product here, it's actually equal to A dot C plus B dot D. You can see that after this dot product, my result is a number, is a scalar. Yeah, this element-wise dot product. Or this is the first formula here. Or you can do this way. This way say that, okay, if I have vector x here, vector y here, and I want to do dot product between these two vectors, and between them they have the angle phi. So to find dot product between two vectors, I simply calculate the length of x plus multiply by the length of y multiplied by the cosine of the angle theta, angle phi, and then I got the same result with this. Okay, so there's two ways you can do it. And the cool thing about this is we call them cosine similarity. This will find uh, the directions, how similarity between two vectors, and a lot of machine learning idea was confirm it. I'll give you example later. So this is a dot product of two vectors. So the dot product is commutative. It means that a dot product with x dot product with y equal to y dot product with x. That's commutative. It's also have distributive. So you can have a sum of y and z, and then you do dot product with x. You can distribute them inside. Associative is when you have the scalar with y here. You can move the scalar outside, just like this. This is semi-normal math, yes. So that's a really nice thing. But the cool idea about dot product is these three ideas. This is so cool because it's so simple and it's so powerful. Let me tell you. So one of the winner projects in the full-time machine learning class, her idea is simple. So her idea is she have a camera, right? How to draw a camera? You have a camera. It's a camera. So the camera capture. Let's say you are wearing some clothes, right? This is the top. This is your bottom. Could be skirt, could be jeans, whatever. So this is detecting the top and bottom, right? The top and your bottoms. Uploading, yeah, uploading. And then let's say this is your shirt. Okay. Yep, this is shirt. And then your question is, she was looking for the same shirt. She's like, hey, I have a really cool friend and she wearing that shirt. And I want the same shirt or something very similar. How do I do it? Okay, so the idea is you have a model, you have a machine learning model. This machine learning model gonna read your image of that shirt and it's gonna give you a vector in like 50 dimensions, in the 50 dimensions. Okay, so this vector is represent the whole shirt, okay? And then she got a data set of all the shirt, yeah, like in Mango, in Uniqlo, in Louis Vuitton, in Burberry, okay, all of the clothing. And she also put them in the model, okay? And each of them will give you a 50-dimensional vector, okay, you know the idea. And she want to find, is there any clothing in the market that look like this shirt? So you do the cost size similarity, you do the dot product between two vectors, you combine, let's say you have 10,000 items in your data set, right? And you want to see which of the clothing look like this specific shirt. So you do cost size similarity between this vector with this, with this, with this, with this, 10,000 times. And each of them will give you a scalar number. And it show you how similarity between two shirts. And that if that number is really huge, then you know that two shirts look similar. And you display that. You're like, hey, you choose a top 10 score. You're like, hey, this is a top 10 shirt that look like the one that you're looking for. And they are, you know, like they are in the shop in like Gucci or Louis Vuitton or like I don't know, Mango or whatever. This idea is super simple, right? But she won the top one in the demo day. I think her name is Natalie. You can check the her videos on the Go to School page. Um, so you can see that dot product between two vectors is positive. Is they have a similar directions. The dot product equal to zero if they are perpendicular. So two vector is perpendicular is mean that they look like this. The angle between two vector is 90 degree. And two dot product of a two vector is negative when they have opposite directions. This one telling me that these shirts are actually extremely different from each other. Yeah. So that's the idea of dot product. Very simple, elegant, but extremely powerful. This idea is like you need to remember this, yeah, because you might use them in your final project. Okay. So the idea of dot product is you can project a vector on another vector. For example, this. So you can see that because I want to find a dot product of x and y, I actually can find the projection of x on y using a dot product. Just like this. You can go home and play around with these numbers. Okay. But now based on the theory, right, I know that the dot product of two vectors is zero when they are perpendicular. Okay, let's try something. Okay, so I have x here is 1, 3. Can you give me uh, a vector y so that the dot product between x and y is zero? Can you give me y vector so that dot product between x and y is zero? So question mark here. Okay, let's try that. Negative 3, 1. Correct. Okay. So dot product between these two vectors are zero because when you project x on y, you can't see anything. It's just one single point. So the cos sine of 90 degree is zero. Yeah. So the whole thing is zero. It's pretty straightforward. Okay, so that is the idea of vector and dot product. Now we are moving toward the matrix vector multiplication as transformer. Mm. So this is a matrix, yeah, n by n. Let's say it's n by n. This is a vector n by 1. Okay, so you multiply these vector matrix together. This is the result. So how we do it? So the matrix multiplications can work like this. Okay, you always taking the column, the row of the first matrix, and multiply element wise with the column matrix of the second matrix. Okay, so A, B is the first row. Let me find my uh, pen, choose a difference. Okay, let's say we have A, B, C, D, E, F, G, K, and you multiply by a matrix. Let's say, can't remember what's the idea. A prime, B prime, C prime, D prime, D prime, E prime, and F prime, G prime, H prime, and K prime. Okay, these are two matrices. The way you do matrix multiplications um, is always you start with the row of the first matrix and the column of the second matrix. So you do multiply them together. So A multiplied by A multiplied by A prime plus D multiplied by D prime plus C. Okay, so not the D here. We do it. Okay, A prime B multiplied by D prime plus C multiplied by G prime. Okay, this gives you a number. Let's call this number alpha. This gives you one single number over here. This matrix is 3 by 3. This is 3 by 3. So the end result of this matrix would be 3 by 3. You know why? Because for two matrices to multiply together, this number and this number have to be the same. And the end result would be this number and this number, okay? That's how you do it. So A multiply A by B. Okay, let's do the rules here. So for the matrix, A by B, okay? A by B multiplied by matrix C by D. These two matrices. For these two matrices to multiply together, A and B and C, the condition is B have to be equal to C, and the result matrix have to be A by D. Okay. So this one give you one single number over here, and you keep going, right? So this one and this one will give you this number over here. This one and this one will give you a number over here. You can keep going. So this one and this one will give you a number over here. This one and this one give you a number over here. So this is how you do the matrix multiplications. It's a bit messy, okay? So let's look at this one. This one is 2 by 2. And this one is like 2 pi 1. So I know for sure that 2 here and 2 here is the same. You can multiply them together. And the end result will be 2 by 1 because we take the first number here, the last number here. So the end result will be 2 by 1. Yeah, and you take the row here, multiply the column, give you this number. And the row here multiplied by this column, give you this number. Okay, so A multiplied by x1 plus B multiplied by x2, give you the first number. c multiplied by x1 plus d multiplied by x2 give you the second number. It's a bit confusing, so you have to go home and actually um, read more or actually do more exercise regarding the magic multiplications. I hope it makes sense. And at the end of the day, you take out the x1 at the scalar over here and x2 at the scalar over here. So you got two new vector, yeah, AC and BD. Perfectly anything. Yep. So this one, surprisingly, from here, so you have the original vector x1, x2. You multiply by a matrix, a special matrix. At the end, you got this new thing here. X1 multiplied by this vector equals plus x2 multiplied by this vector. And you call these two vector is two new unit. Yeah. So what does it mean by this? It means that from a original unit vector, you multiply by this matrix, it transforms the whole vector to a new dimensional space. Does it make sense? Yes. From the original dimensional space, you multiply by a matrix, it transforms this original vector to a different dimensional space with the basic vector is I and j here. That's the idea. So the idea is you have a vector, you multiply by a matrix. That matrix contains some property that can transform a vector to be different. Okay. So let's use this example. You have the a vector x. You got a special m vector. Okay. And then you apply a dot product into m. Okay. How do I show it? I can show it. You can see that, so I here and j here from the original matrix, it was rotating 90%, 90 degree anti-clockwise. Okay, so this matrix is allow you to translating a vector 90 degree. So what about this one? This one allow you to sharing the vector in these directions. So the I is the same, but the J is which from here it was shearing to the right. So this matrix allow you to do it. Okay, that is the main idea about matrix transformations. Okay. This idea is not too important. It's just showing you the concept of like matrix multiplication. What does it mean? So far in high school, you learn about matrix multiplication without understanding why. Like, and you know the rules, but you don't really know the purpose, right? So you have a matrix multiplied by a factor, you got a number coming out from it. You're like, hey, it's different. But I'm sure that by now you know that if you have a vector here, just a point, and you want to transform that to be something different, like you can rotate them, you can shear them, you can scale them up. So imagine you have an image contain all the points, right? Let's say a face, and you want your face to be a bit bigger, rotating left and right. You can multiply by a special matrix, do that for you. So this is how Photoshop, this is how all the image manipulation software works, right? It's got the image, right? And it actually applies some matrix multiplications, and it transforms the original image to be something different. Um, okay, like this, yeah. Hmm, transform with error. Okay, I don't want to multiply by that. Let's choose difference and Okay, so we have some x and y here. I try to show you. Let's not have this. Yep. So we have we have some like random point here, yeah, x and y. It was spacings apart to each other like this. So this is all your original points, right, in two-dimensional dimensions. And then you want to transform these points into a new dimension by apply the matrix transformation to them. So let's do it. So once I scatter them, let's do it. It's a bit difficult to see, but you can see that these points were rotating 90 degrees to the anti-clockwise, right? Let me not showing the scattering x and y. You can see that from the original point, it was like this. I rotating 90 degree anti-clockwise. So it's looking like this. Okay, so let's try a new magic transformations. So this one is shearing, right? So I apply and it translate my unique factor to be shearing to the right. So if I apply this to um, my new point, so let's draw the points again. So this is my original data. So I apply the matrix transformation of shearing, which I display the x original point. You can see that from the original point, it was shearing to the right like this. Yeah, it was shearing to the right like this. It's applied to every single point in that dimension. This is a really powerful idea. Eventually, you guys will learn about OpenCV, and OpenCV is just like a library in Python. You can manipulate images. You can like rotate them. You can do all the stuff with them, just like Photoshop, by applying the magic multiplications to your image. This idea is very powerful, so remember that. So you can actually rotate them lockwise the um, by the angle C, just like this. This is a magic multiplication allow you to rotate lockwise. Okay, let's try that. So I have a theta angle to be pi divided by 3, so 60 degree. So apply to that. You can see that this is my original vector x here. So after apply this magic multiplication, my new vector now was rotating exactly at 60 degree clockwise. And this is the formula for shearing, right? So if I apply this to my uh, to my uh, to my graph, then my all my data point was shearing to the right, just like we showing you before. You can try different value and see what happens. Okay. So let's say you choose some of the column, they are independent to each other, just like this. The one, negative one. Then you actually swashing them into one single line. Okay. So from all the blue line here, you swashing them to one single red line. Let me just show you the X and Y. So from all the point here, you just swashing them into one single line, just like this. Because you are using the magic multiplication that linearly dependent inter columns, one, negative one. What's the cool thing about this? You can combine together to make a series of transformations. So this is original vector. Um, and first you want to rotate them, and then after that you want to shear them, right? So you can combine them. You can like multiply rotations with shearing first to create a new matrix called composition. Composition is just combination between all the transformations. So first it rotate and then shear. Um, so this one, you can see that this one and this one is exactly this one. So it's up. do two magic multiplication, you can do one and still have the same effect. But the thing is, magic multiplication is not associative. It is not commutative. So you can't do shearing and rotating and shearing. They are have the different effect. Um, so let's see that. Okay. So we have rotating here and shearing here. So this is shearing and then rotating, and this is rotating and shearing. Okay, so we're gonna do that. So the first one is shearing and rotating, and then we're gonna do rotating and shearing. Let's see the difference. Okay, you can see that that's totally different here. So definitely the magic multiplication are not commutative. So you can't do A multiplied by B equal to B multiplied by A. Okay, so hmm, let's keep this topic. This is the bonus topic. Yeah, we will go back if we have time. Bonus. So you can go home and read this topic if you want to. Yeah, there is three topic that I think you should go home and read that. So determinants. So I can quickly tell you the idea of determinant. You can understand that determinant is just the area between two vector. Okay. At the same time, determinant is really important if you want to find the inverse matrix of a matrix. So this is a formula for determinants. This is useful, very useful. So imagine, let me talk about this part. So we have, let's say we have some linear equations like this. So this is a hyperplane equal to y. This is the second equation. The third equation equal to x1, x2, and x3. So can someone, okay, so then we can like convert them into this form, right? So we have a vector x here multiplied by an m vector here. It gives you x1, sorry, y1, y2, and y3. Can you quickly tell me that this is really similar to the idea that we actually did before? We talked about this before. So why is that? Can someone tell me? Can someone relate to this topic to the previous topic in this one, right? In this one, yeah. The correct, yeah. So the idea for this is you have x1, x2, right? These are two of the features. And then you want, let's say you want to do linear regression, right? So you need to multiply, you need to find W1 and W2. So X1, the formula of the line, of the best fit line would be um, X1 multiplied by W1 plus X2 multiplied by W2 plus a bias, right? Equal to Y hat. Y hat is a prediction, right? And then eventually you want to find the loss function. Remember, talk about that. Loss function between your prediction and your true label. So your true label here is y. Yeah, you see y hat the prediction, and then you try to minimize that, minimize by this log function. Okay, this is the idea of this, and now you can see that. How do I click the mouse? Okay, perfect. So you can see that this idea is very similar to this idea. Yeah. So you have x1, x2, x3. You have three features. Yeah, and then you multiply by some numbers a b c. It's give you y1 here. So you can imagine that this is exactly the linear regression with multiple variable. So you have these three features. You want to find some weight, yeah, some weight of A, B, C, D, E, F, G, H, I, so that when you multiply them, it's going to give you the prediction that you want. So this is the formulas, and then in short, you can rewrite them in this form: linear regression. So linear algebra. So this can be very convenient, right? So you can solving for x. So in high school, right, this is usually the equation you need to solve, right? You have some numbers like say y1, y2, y3. You have some number for a, b, c, d, e, f, g, h, k, g, h, I, and you need to find the variable x1, x2, x3 in high school. So what you want to do, you want to rewrite them in this formula. This is your target, yeah? You want to find x1, x2, and x3. So what happened is you can rewrite them in the form m multiplied by vector x equal to y. And then you need to find the inverse matrix of m. So you multiply by both sides. So any matrix multiplied by the inverse matrix equal to the identity matrix, we say I here. So I would be the identity matrix. Identity matrix is exactly how do I exactly one in the diagonal and 0, 0, 0 everywhere else. Yeah. This is identity matrix of for this is I, okay? I look like this. And then you multiply by y. So y, I gonna multiply by the inverse matrix of m. It's gonna give you x. So you're already solving for x. This is how you're solving for x for your like equations back in high school. And you need to find the determinants of m, because if m determinant equals to 0, then there is no inverse matrix of m, then there's no way you can find the x gonna satisfy this equation. So that's why determinant are actually important. Okay, you can have a look at this. Uh, so yeah, so you have y here is 6, 7, and m here is 2, 2, 1, 3. And you want to find the inverse matrix of m like this, and you multiply by y, okay? This is your formula. So y multiplied by the inverse matrix should give you x. And then that's it, that's solving your problems. Um, so let's double check, yeah? Let's double check. So your y is 6, 7, right? So technically you have the equation look like this. So 6, 7, and you want to find this equation. So 2x 1 plus 2x 2 1 x 1 plus 3x 2. And you are trying to solving for x and y. So x1 and x2 here. So the answer is exactly this. So the answer is 1, 2, x equal to 1, 2. So this is how it's solving for x here. You can double check. Yeah, so 2 multiplied by 1 plus 2, 4, 6. So 1 multiplied by 6 is 7. Perfect. This is correct x. You can see it here. And this is how you're solving it in NumPy. Okay, so pretty straightforward. I know it's a bit overwhelming because you forget about all this already. So I hope you have time to actually go home and try to revise this um, informations. Trust me, you don't need to like understand the coding so much. You can play around with this program for you to learn, for you to play around, not for you to like memorize that. So we are learning math in this way. Yeah, we don't ask you to remember all the syntax. We're asking you to remember the idea of like linear algebra. Okay, so there's two quite advanced topic is determinants and agent value and Bayesian vector here. So if you have time, you can go through them. So okay, so let's have a break for like 5 minutes. Let's have a break for 5 minutes, and after that, we're gonna go through the notebook for calculus. Okay. To me, I think this topic is also very important, maybe even more important than linear algebra. Mm. So let's have a break for 5 minutes because get back at 8:15 p.m. Okay. I actually find calculus actually way easier and more interesting compared to linear algebra. Linear algebra is like half really boring. It's like okay, it's like okay, you need to know the rules, right? It's a trick to make things faster and more like organized. But calculus is more fun. It's more like sensible to learn. So definitely you're gonna have a lot of fun with like learning calculus. Okay, so let's get back at 8:15. Okay. Um, if you have a question, that like send me in the chat. Okay. Okay, everyone's here. Testing, 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 testing. Can you hear me? Testing, testing. Yeah. I remember you guys, like the for hardworking guys, actually love to learn math at night. Yeah, learning math at night was like really tough and challenging, but yeah, you guys doing it. Good job. Okay. I'm still sharing my screen here. Okay, recording is still on. Okay, perfect. All right, so let's start with the calculus, right? Okay, this is super important topic, right? This is one of my favorite topic. Learned this last year. How? Oh, the uni actually teaching machine learning or just calculus. Yeah, calculus is interesting. Why? Because for machine learning, right? We understand that we need to find cost functions, right? Cost function telling you that the model is doing well or not well, yeah. So this is a cost function, or we call that objective function. So you want to either minimize it or maximize it, depends on like what you are doing. And that function is a function, it is a function, and you want to like minimize that, right? So at the end of the day, the whole thing just a big bunch of derivative in calculus and kind of descent. Um, so let's see how we do it. So as I talk to you guys about this special function hash here, hash are mapping from your input to your output. And at the end of the day, after you get the output predictions, you want to compare that to your true label. That is where the cost functions come from, right? You want to find the mapping. So f and hash functions f function is mapping from your input to your label. Okay, one to one, just like this. Okay, this is machine learning. Technically, this is the whole thing about machine learning. You find a function to mapping from your input to your output, and you find a way to minimize a loss function. Okay, let's do it together. I have to be Tom Win again. Okay, now I'm Tom. Calculus. Okay, let me have a. Okay, all right. So when it's come to calculus, the first thing we learn is differentiations are derivative, right? Okay, don't worry about this part. This part telling you that, does anyone remember what is differentiation and what is derivative? Surely wrong. Imagine you have some like functions, right? It's like of functions. Let's say like this. Yeah, these are functions. This is your y, this is your x. This is your x, this is your y, this is your functions. And technically the idea of derivative is to find the rate of change, to see how much y gonna change if we are increasing x a very small amount. So what does it mean by this? So imagine I want to find a derivative at the point x0 here. So x0 gonna corresponding to a special I0, right? So in the theory, you want to find if I increasing, okay, the question is if I increasing x a bit plus epsilon, right? So epsilon is a very small number, okay? Just remember this. Epsilon is a super small number, could be 0.00001, for example. Epsilon is a very small number. And then This gives you a new, this is um this is equal to f of x0, right? So y0, your original point, equal to f of x0. Now it's gonna be your new y1, okay? The new y1 equal to what? F of x0 plus epsilon. Yeah, does it make sense? So at the end of the day, to find the rate of change, you need to find rise over run. What does it mean by that? If you zoom in, right? Let's say you zoom in this angle, then let's say this is the angle. So this is your x0. This is your x0 plus epsilon. And this one is your f of x0. And this one is your f of x0 plus epsilon, right? So you know that the differential or derivative of this one would be rise over run. What is rise over run? Rise over run would be the vertical rise. This is rise, the vertical over run. Run is horizontal, this part. So the derivative of something equal to the top, the red part over the yellow part. Okay, rise over run. Okay, this is the derivative. So let's calculate that. Okay, so you can see you know that rise over run, right? So to find exact how much is the red part, you have to have this minus this, right? So it will be f of x0 plus epsilon minus f of x0, right? This is the red part. You having this minus this give you this. Okay, this point minus this point give you this length of the red part and overrun. So you want to know how long is the yellow part. So this yellow part is easy. You having this minus this equal to exactly epsilon. Okay, and epsilon here is the same thing with the triangle x. Okay, it's just the same name. So this is the formula to finding a derivative. Um, and let's say we know that let's this this um this x this f equal to 3x. Okay, let's try to find the derivative at the point uh x equal to, let's say, 4. Okay, so if you apply these formulas, rise over run, you know that it's going to equal to f of 4 plus epsilon, a very small number, minus f of 4 over a very small number. So at the end of the day, it's going to equal to f of 4 plus f of epsilon minus f of 4 divided by 3. Uh, so, okay, so this one and this one is gone. And f of epsilon, okay, and f of this one, the whole thing will be equal to exactly 3. So you know that the derivative of this f function equal to 3 anyway. Yeah, so f of derivative equal to 3. So you're proving that the derivative of at any point of this function equal to 3. So that's the intuition of the derivative. This just measure the rate of change of a functions. Um, so let's say we have this function more complex than before. So minus 2 of multiplied by x squared plus 3x. So the derivative of this equal to, if you remember the rules, right, equal to minus 6 x squared plus 3. Okay, and then if this one equal to 0, then you're gonna find these extreme point of like the function x1 x2, and then let's go through this example together. We see. Um, so we have all the x here. Okay, this is a formula you having, right? It's exactly like this. So minus 2x power 3 plus 3x. Okay, so minus this one. This is your f function, and then you having this derivative. Okay, you got the epsilon, very small number. So this is the formula you have having before. This is formula you are having before. Um, so um, so f of x plus epsilon, just like this, minus by fx over epsilon. This is how you find the derivative of f. And this is how you find, okay, let me write down the formulas again. Okay, so you know that f, you have x0 here, you have an x0, you have a special functions, and then using that functions, you can find y0. Um, and then you want to apply that derivative of this point, yeah, to find a, because at the end of the day, you want to find a tangent, right? So the derivative is just a tangent at that point, okay? The tangent of this point. And the formula for a tangent will be y equal to a x plus b. Okay, so the derivative of that point is exactly a. Okay, so we have x0, and then you plug in the function, you have y0, and you got the function of finding derivative up here, and then you plug in your position x0, it will give you a. A is the slope of the tangent at the point x0. Okay, and now you want to find b. How you find that? Easy, right? Because you already have x0, you already have a, you already have y0. So to find b, b equal to y0 minus a x0. Yep, exactly like this. So you give you a and b. So you got the whole formula of the tangents. Okay, let's try to like display that. So you can see that the blue line is the function here, negative 2x squared plus 3x. Okay, and your x0 I choose it to be negative 0.5. Okay, it's right here. Draw again. So this part is exactly negative 0.5. And you can see that we are successfully finding the tangents of A and B. So this is the formula of a tangent. So y equals to 1.5. Don't worry about this long number, just like some actual number at the end. So 1.5x plus negative 0.4. So it's your tangent, which is interesting. But there's something special about this, yeah? So when your tangents, when your derivative function equal to 0, if you solve for x, you got these two special points, okay? So let's plug in these two special points and see what happens. So if I plug in the, so I changing x0 to that, so 1 divided by numpy square root of 2. Okay, let's run that again. Oh, so if when I plug in this specific point, at 1 over square root of 2. I got this tangent. Can you tell me what is special in this tangent? What is special for this tangent? It's horizontal, right? And what's the formula for this? So this is B, this is your B. So A equal to 0, x plus B. So when the line is horizontal, A equal to 0. You can see that A here is a very, very small number, nearly equal to 0. So negative 4 point something power negative uh, 0.06. So it would be like 0.0000004. It's a very small number, nearly 0. Okay, actually it's 0 in this case because it's supposed to be the maximum point, right? So when you are solving for tangent equal to 0, you have to special point the maximum and the minimum. At this point, the tangents or the slope will be equal to 1, okay, equal to 0. Okay, this is your tangent. Let's try for the other point. So even do get negative here. Okay, so now I'm actually at the minimum point. Okay, the formula is similar. So my formula here with the slope equal to 0, and this is my B. Okay, that's cool, that's cool. But can you tell me, this is easy questions, can you actually tell me that if I choose my X here, yeah, my tangent would be here. Oh, not this. My tangent, my tangent would be like that, okay? Is it a negative number or a positive number for the slope? What is A here? So y equal to ax plus b. What is A here? A is a negative number or positive number? Can you tell me? It's a negative number. So let's try that, okay? So this point we is 1 here, so it's negative 1.5, something around that. Let's try that. So if we put negative 1.5, okay, so somewhere here, you can see that my slope is negative number, okay? And similarly, if I put my tangents x0 at 0.5 here, then my tangents is this way. Yeah, it should be positive number. So let's try that. Put negative 0.5. So I have this tangent, and you can see that my slope is positive, right? So the rules to remember is this. So if you go from the left to right, if the tangent is going, okay, you go from the left to right, right? If the tangent was from the top to bottom, is a negative number. And if you go to left to right, if it's going from the bottom to top, it's a positive number. Why is it important? It's super important idea, yeah? Why? Imagine this is your loss function, right? It's your model. You are trying to minimize the loss functions. So after you are doing some derivative, right? Let's say here, you are at here, and you want to minimize loss functions. So you want your model, sorry, you want your, let me find the word for that. You want to find the minimum of the slope function, right? You want to find this point. So at this stage, your slope, your A, is a positive number, right? A plus. Okay, and you want to find the minimum point. How do you do that? So you want to find the derivative of the loss function in respect to your, let's say your weight, yeah, equal to whatever. Yes, this is how you do derivative. And then you want to change the weight so that it's actually reaching the minimum. So this is your step. So W equal W minus alpha multiplied by derivative of the last function in respect to W. And we call the whole thing here is gradient descent. This is the most important idea of machine learning. We're gonna learn that later on, but I'm gonna tell you early now. That's why calculus is so important because now you understand that this is your loss functions. You want to minimize that. Then if actually positive, then you minus the positive, you are going these directions. Yeah. If actually a negative slope, then you can minus negative, then you are going these directions. So depends on if you are positive or negative at the slope. You are reaching, you are moving toward this minimum point. That's the whole idea of derivative and gradient descent in machine learning. This is how you are keep update the weight so that your model can become better and better, perform better and better throughout training. Let's try to like optimize the loss function. Let's try to find the slope. Where is it? Is it positive, negative, and then minus, regardless, minus the learning rate. This is the learning rate, how fast you are moving. It's the learning rate really, really big. It's a move really quickly, but sometimes overshoot, right? If the learning rate is really small, you can take a small step at a time, small step. So every time you are learning, you can do one small step, update to the right objective until the end, until reaching the minimum. And you're gonna like stop there. So that's the idea of machine learning and gradient descent. Okay, cool. All right, so this is the rules. This is the one that we actually want to talk about today. So we have some rules, right? So some rule is say if you want to find the derivative of a sum of two functions, you find the derivative of each of them. That's cool. Then we have power rules. So if you have a function fx equal to a x multiplied, sorry, a x power b, then to find the derivative of that, you just keep x here, so keep a here as a constant, and then you bring b at the front, multiply them together, and then you have to minus the power by 1. So you have abx power b minus 1. So for example, if you have like if your x equal to 5x squared, then your derivative of that would be you keep the 5 here, you move the number 2 outside, and you do 2 negative 1. So at the end you have 10x only. So this is the result, yeah. Follow these rules. I hope it's straightforward. And then you have the product rules, right? So you have two functions multiplied together. Then you want to find the derivative of the first function and keep the second function the same. And then plus the product of the first function stay the same and the derivative of the second function. So you can imagine that these two functions take turn to find the derivative. Okay, and this is the interesting rule. So you have if you have a quotient, so a over b, then you can for the numerator you find the derivative of the first function and keep the second function the same minus the derivative of the second function keeping the first function the same over the square of the second function, just like this. Okay, got to remember that this is some basic rule of derivative. You can always like refer back to this. later on. And the most important rules is the chain rules. So let's say you have a function f and you want to find the derivative of f over h. You can actually break the function down, right? So if you have f equal to f of g and then g equal to g of h, then you can do derivative of g of h equal to the derivative of f in respect of g multiplied by the function g in respect of h. So what does it mean by this? Um, so let's say you have f functions equal to uh, 5, 5, 5, try to find something interesting. 5x dot 5 h, okay. 5, 1 over h square plus 5 plus 3. Okay, so if you have a function here, and you can see that if you want to find the derivative of f in respect of h, it's a bit complex, it's a bit complicated, yeah? So you can say that, hey, let's g equal to h square plus 3. Okay, so your f equal to what? Your f equal to 5 of g. Yeah. So what you can do, you can, hey, this is pretty cool, right? So if I want to find the derivative of the original function, which is df over dh. Okay, this is the original derivative. Instead of do these complicated things, I can say, hey, it's actually equal to derivative of df over dg multiplied by derivative of the function g in respect of h. Okay, so this one's mean that if I can find this derivative, the g over the h, then the whole thing here will become 2h. Yeah, and this one, if I can find the derivative of df over dg, the whole thing here will become what? So negative 5 g squared. Okay, so you know that now I can just plug in this one to here, so to here, and this one to here. It can give me the derivative of this one, of the original function. So this is really not really nice, right? Imagine you have very complicated functions. You can just like break them to a very smaller function and then try to find the derivative of each of them and then combine them together at the end. We're gonna have an example later. Okay. So there's a few derivatives right here. You can go through them. It's pretty straightforward. So let's do this example, right? We don't have much time left, so let's go through this together. So let's find this derivative. So how do we do that? So you remember that this is applying the quotient rules, right? So derivative of a over b equal to what? Can you tell me? B squared. Uh, it's over here, yeah? This is the function. Let me write that for you guys so you can remember that. And you can just find the derivative of the first one, right? First one, so a derivative multiplied by b minus a multiplied by b derivative. Okay, let's go down here. So let's check. So to find the derivative of this, you actually square at the bottom, perfect. And then you have to find the derivative of the first term, which is 5 multiplied by x power 4. And then you keep the thing here, b is the same, minus and then you keep the first term the same, x power 5, and then you have to find the derivative of this term is 3 only. The constant is 0, remember, the derivative of constant is 0. So equally, you have the 3x power 5. This is the result of that, and then you can simplify them, you can multiply them inside, and then you can simplify them to be this. Okay, that's straightforward. What about these functions? It's long. Okay, this is sigmoid. This is sigmoid functions. So sigmoid function is one of the most famous activation functions in machine learning. It's gonna look like this. This is a sigmoid functions here. So it's never reach 0 here, it's never reach 1 here. It's go from -1 and cutting at 0.5 at the vertical axis and reaching 1 here. This is a normal sigmoid function. So these are these functions. So the find derivative, it's a bit complicated, so you can do the change rule. So you can say that instead of doing derivative, I can call G. So I can call G equal to the bottom one, right? And this one is equal to H. Okay, H equal to this part, and G equal to this one, and then I can write the whole thing equal to 1 over G. Okay, I call it this to make things easy for me. And then I can apply a change rule, right? To find the derivative of the original variable, I can break them into different functions. So I can find the derivative of this function in respect of G. And then I can find the derivative of G, this function, in respect of H. Okay, over here. And then I can find the derivative of H in respect of Z. So when I multiply them together, it's become derivative of sigmoid function over the Z. Okay, so you can follow this part and try to find the derivative of each of them. So the derivative of sigmoid over G is easy, right? So this is the power rule. So G, this one equal to G -1, right? So -1 here over multiplied by G. So this one multiplied by G -2. Uh, power of -2 can be bring down to G2 like this. Okay, straightforward. And then the derivative of the function G in respect of H is just equal to 1. This one is become 0. This one become 1. So it's 1 here. And the derivative of this equal to this rule. Yeah, the derivative of e power x equal to e power x. Because we have the negative inside, we have to bring them out. Okay, so it can be negative of e, negative power negative of z. And then you multiply them all together, you're gonna got the result. Yeah, multiply all together. So it's gonna become like this. So this is very interesting, right? The derivative of a sigmoid equal to the function sigmoid multiplied by 1 minus sigmoid. This look beautiful. It's like derivative of a function of this function equal to the combinations of that function. This is interesting. You can follow the map and try to tell me if you have any questions. Okay. Let's see how far we are trying to reach. Okay. Okay, computational graph, right? This is the idea how you implement the derivative inside your computer. Your computer, especially TensorFlow, this advanced platform, they're gonna find a derivative for you. So how do they do that? So imagine you have a special function this. The whole thing here can be represented by a computational graph. Okay, so x uh, multiplied by 5 become like this. That's 5. And x multiplied by 3. So this is the operations, right? So x multiplied by 3 become 3x here. and then plus 9, so the whole thing becomes 3x plus 9, and multiply by 1 over x becomes like 1 over 3x plus 9. Okay, so, and then the whole thing here multiply by x power 5 equal to x power 5 over 3x plus 9. Okay, so this is a computational graph, right? So imagine that x is your feature, x is your training data, and after you pushing through your equations, could be linear regressions or some special model, you get the result y hat. So y hat is your predictions, right? So x could be a number, could be a vector, could be a matrix. And then this is how you do forward propagation. You calculate all the formula to get your predictions. This is your predictions. This is your label. With this, you can find loss function, right? This is your loss function. And then using that, you're gonna calculate the derivative of a loss function in respect to the weight. So all the things here, all the weight inside, make sure that you're changing the parameters inside the model. And from that, you update the weight in respect to the current descent rules. So you update the weight based on if the derivative is positive or negative, and how fast you want to update the learning rate. Okay, alpha is learning rate. So this whole thing of machine learning, right? Um, the idea of calculating the derivative of this, you can uh, the whole thing here, the whole idea here is to calculate the derivative. So you have the conditional graph already. In here, they can actually going backward like, hey, what is the derivative of this in respect of this? What is the derivative of this in respect of this? What is the derivative of this in respect of this? What is the derivative of this in respect of this? They can calculate every step back, okay, to find the derivative. That's why they can find this function. That's the idea of like machine learning. So this is useful for computer. The computer can representing the whole function by computational graph, and with that, they can also calculate derivative, like in respect of each of them, just like this. Okay, so let's do it together. Let's do one example, and then we can go home, all right? So what is the original formula? The original formula is this, right? Let me write down. The original formula is x equal to x multiplied by 5 over 3 uh, over 3x plus 9. Okay, so in here, this is your original formula. We're gonna follow this to create our functions, all right? So you can say that, all right, so let's call a equal to x power 5 and b equal to 3x here, 3x, and c equal to b plus 9, okay? So you got the whole thing here equal to b. And then d equal to 1 over c, so the whole thing here, c equal to the whole thing here. And then you serve this value into cache, okay, to remember them. And lastly, you want to multiply by a, d multiplied by a. Yep, because you got this one, you have to multiply by a. So this is your a, this is your d. You have to like put them together to get the final result f. And this is your forward propagation. So forward propagation is you have x, and then you try to find the value f here. Just go through the graph. You try to calculate the value f. After you get that, and then you call the function to get f and the cache. So why you case them? Because when you want to find the derivative, you need to have these intermediate values, right? So it's useful to save them because you don't want to calculate them again because it's a waste of time. You want to save the case, yeah? And this is a step of doing backward, right? Okay, let's have a look at this together. Okay, so derivative of b, this is b, right? In respect of x, definitely 3, right? So derivative of b in respect of x is 3. Okay, we have it. Derivative of c in respect of b. Okay, this is function. Derivative of c in respect of b equal to what? 1, right? 1, but this one is a function. That's why you need to find derivative of this. So the derivative of c in respect of b equal to derivative of b. Okay. All right. Let's find the derivative of d. Derivative of d equal to this. So this is c power negative 1, right? So at the end, what's the derivative? You want to keep negative 1 here, multiply by c power negative 2, and then also multiply by derivative of c prime. Okay, have a look at this. So negative 1 here multiplied by c power 2. It's negative 2 because they actually already divide that. The whole thing here multiplied by derivative of c. Okay, it makes sense. Derivative of a, okay, this is more easiest one. Derivative of a in respect of x equal to 5x and multiplied by, sorry, power 4. Okay, straightforward. And finally, we have f. So the derivative of f equal to, this is the change rule, right? Derivative of a power rule of a product of two numbers. Say f equal to a dot b, right? So derivative of f equal to a derivative. We call the prime here a prime multiplied by b plus a multiplied by b prime. Okay, this is exactly what you want, right? So derivative of f equal to derivative of a multiplied by d plus derivative of d multiplied by a. Okay, that's pretty long, but this is should find you the total derivative of f in respect of whatever is the result of x. So let's do it. So after you do forward propagations, you calculate f, and then you want to find the derivative of f in respect of x, doing backward propagations. Let's do it. And these two numbers are the same. Okay, where I get this number from. This number is the one that we did before together, remember? This one, yeah? So when you find the derivative of this is equal to this formula. So when I plug in this formula to the x, what's my x? I choose x equal to 1, right? So if I plug x equal to 1 into this formula, they're gonna give me exactly 19 over 48, okay? I know that by using the math formula. Now I want using my algorithm to see if I can calculate the derivative correctly using chain rule. And these two numbers are the same. So it's telling me that my derivative using chain rule is actually correct. It's a good news. Okay, so whew, all right. So for the sigmoid, this is sigmoid function. Yep, this is sigmoid function. I already mentioned to you guys before. Um, and I have these two functions, forward and backward propagation. So I want you guys to go home and follow similar step here. So I will be calculating the derivative of sigmoid based on math already. Then the whole thing would be have a very similar process, right? To calculate the derivative of sigmoid using the chain rule should be similar, very similar. You can look at this as well as example. Okay, so I want you guys to go home. This is your homework. Yep. try to find derivative, try to finish this function forward and backward. And also show me that actually is correct. But print out your forward, you have to calculate forward and then you have to calculate backward. And show me that you calculate the correct derivative by checking, by plugging in an x, and then use this formula to calculate your derivative. Okay, you can check in using the math formula, and you can check that using your function forward and backward. Okay, any questions? Does it make sense? I know it's a bit challenging for sure. How to pull? Okay, so yeah, definitely it can be really useful if you can like try to finish the question by tomorrow. So tomorrow I will give you guys the solution. I go through the solution. Um, and then we will talk a bit about this partial derivative. And then we're gonna have a lab. Okay, we have a fun lab of machine learning. Any question? Any question before you leave? So you have a homework, yeah? Any questions? So you have a homework tonight. You can do this question, and then for tomorrow we'll talk about partial derivative, which is like very similar idea with derivative. Partial derivative is just like a function with multiple variable. So you have to like find the derivative in respect of each of the variable. That's what we call it partial, because it's not full. So the full derivative equal to a partial derivative of each of the variable. Then yeah, tomorrow we're gonna do the lab together. It'll be fun. Okay, thank you guys. I upload this lecture recording to the spreadsheet. Um, and then yeah, if you have any questions, please send me on Discord. Okay. All right. Good night, guys. I know that today is a bit tough because so much math. But from tomorrow, no more math, all right? Tomorrow, promise, no more math. We're gonna work on machine learning. Okay. Good night. All right, guys. Good night. Bye.